Hello and welcome back. Now that we learned how to operate with infinity, I think we're ready to explore finding asymptotes. I'm going to get started with vertical and horizontal asymptotes. And as an example, to illustrate the whole process, I chose the equation of a rational function y equals x plus 1 over x minus 2. So I'm going to write the function, the equation one more time. Now, in rational functions, we always have to look out for the restrictions. And we're going to say that x minus 2 has to be different than 0, which means that x must be different than 2, which means that the function is not defined at 2, because at 2 the denominator is 0. And now we're thinking, what exactly happens at x equals 2? What is the behavior of y? What's the shape of the graph around it? So we're going to look at it algebraically first. And to analyze this, we'll approach x equals 2 from the right-hand side and x equals 2 from the left-hand side. So if x approaches 2 from the right-hand side, then as an example, we're going to take the number 2.0001. And we will substitute, or we'll find the value of y at 2.0001. So for instead of x, we are going to write 2.0001. So 2.0001 plus 1 divided by 2.0001 minus 2. So the value of y would be 2 plus 1, 3.0001 divided by the difference between 2.001 and 2 will be a very small positive 0. So if you use a calculator to perform this division, then the answer would be a 3 with 4 zeros, 3,000. So imagine that 2 from the right can be even closer to 2, which means more zeros in between. So the more zeros in between, the smaller 0 this becomes, and a bigger y this becomes. So we are going to say that in this case, the y values will approach infinity. So as x approaches positive 2 from the right-hand side, y approaches infinity. Now, what happens when x approaches 2 from the left-hand side? Well, let's take an example of an x value. 2 from the left would be 1.99999. So for the y value, we're going to say we have 1.99999. You can add more nines if you wish. But when I use a certain number in an equation, I keep the same value throughout the equation, which means if I substituted 1.999 with 5 nines after number 1 for this x, the exact same thing must be here as well. Now, plus 1 divided by 1.9999. How many nines do we have here? 5. And then minus 2. So that will give the value of y equal to 2.99999 divided by the difference between these two will be 0.00001. And remember that we are subtracting 2, right? So that would be negative. So in other words, you can look at it as the number 3 less than 3 divided by 0 minus. Now remember, 0 minus is a negative, right? Use a calculator. And the calculator will tell you that the answer is 29999 and a negative because we have a positive divided by a negative, which will give a negative. Imagine that you can get even closer to 2 from the left-hand side, so more 9s in here, which means more zeros in the denominator, which means a bigger y. So we are going to say that in this case, a bigger negative, obviously, the y values will approach negative infinity. So what does that mean in terms of the asymptote? What I'm going to do is I'm going to draw the axis here. Okay, and I will mark x equals 2 right here. And when we approach number 2 from the right-hand side, we are told that the y values will go all the way up to infinity. And when we approach 2 from the left, the y values will be heading towards negative infinity. Okay? So, would x ever be equal to 2? And we're going to say, it's not allowed. So what exactly is happening then at x equals 2? An asymptote is born, a vertical asymptote, because at x equals 2, the y values will either approach positive or negative infinity, and the y values will never ever actually be calculated based on x equals 2, so the graph will never cross this line. So this will be an untouchable territory in the form of a straight line. And that's how vertical asymptotes are born. And in the meantime, the operations with these fancy numbers, so close to a number from the left and the right, help us describe the behavior of the function as well. Now, let's take a look at horizontal asymptotes. Horizontal asymptotes, as the name says it, are horizontal lines, right? Now, horizontal lines means that the graph will get very close to this, or horizontal asymptotes means that the graph will get very close, but will never touch the asymptote, okay, or the horizontal line. Horizontal asymptotes happen when the y values stay the same or remain static or approach a constant number as x becomes very big or very small. So as x approaches infinity or x approaches negative infinity, the y values will remain constant here. They'll be on the same line, okay? Now, how can we calculate the asymptote? So one way would be, let x be infinity. So let x approach infinity. Let's define the territories here. It's all about territories, you know. So we have the function y equals x plus 1 over x minus 2. If x approaches infinity, then we're going to say the y values will be infinity plus 1 over infinity minus 2. Or the y values will be infinity over infinity. And now we're pausing for a second thinking, wait a second, didn't we say this doesn't exist? Well, yes, we did. That means that we cannot substitute x by infinity because we get an undefined expression. So we are going to choose a clever way to define the values of y as x approaches infinity. So we are thinking, okay, so what made this expression undefined? The presence of infinity in both numerator and denominator. So what brought infinity in the numerator and denominator? Well, the presence of x in both numerator and denominator. So x became infinity, and then that's how we ended up with this undefined expression. So we're thinking, is it possible to simplify that x before we evaluate? So we're going to say, well, let's give it a try. So if we have y equals x plus 1 over x minus 2, we can simplify in a fancy way. And I want you to listen carefully here because you may or may have not done this before. We're going to take x as a common factor. Obviously, x doesn't appear in both, but we'll take that out. So if you factor out x, what we have left from this term is number 1. So x times 1 will still give us the x we had. And now we're thinking, how about the other term? So I must think this time, what should I put in here? So after multiplying it by x, I get number 1 because I can't change the expression. We're simply factoring, right? So in order to help you with this, you probably have figured this out already. I want us to think this way. If we had 3x plus 6, and you take 3 out, how do you figure out the number 6? I mean, what number 6 becomes? So you can naturally and very quickly say, oh, that's 2. I know, that's common sense. But what operation is hidden behind this? Well, the operation hidden behind this is you take the 6 divided by 3, and that's how you get 2. So in this spot, we get 6 divided by 3. So whatever we had, in our case 1, divided by whatever you factor, which in our case is the factor x. So we're going to say that the missing term here is 1 over x. The same way, we simplify the denominator, or we factor. So we have 1 minus 2 over x. And now we can simplify x. X was the culprit that brought the infinity in both numerator and denominator. So let's see what our expression becomes. Let's substitute x by infinity. So this will be 1 plus 1 divided by infinity over 1 minus 2 divided by infinity. So 1 over infinity will be a 0 plus. 2 over infinity, a 0 plus. Which means that here we're going to have a number slightly bigger than 1. Here a number slightly less than 1. And 1 divided by 1 will give approximately 1. If you were to divide these two numbers, then you would have had 1.00001 over 0.9999. So that will give us approximately a number bigger than 1, which tells us that as x approaches infinity, the y values will approach number 1 from above it. Okay, so in other words, and this is the most important part, we're going to say that the function has a horizontal asymptote, y equals 1. And we'll draw the horizontal asymptote right here at y equals 1. And we're going to label it. I'm going to say this is a horizontal asymptote, everyone. The equation of it is y equals 1. And when x approaches infinity, the y values will be above the asymptote because the y values are more than 1. And when it comes to graphing the function, now we're going to say, oh, so the behavior will be this way. And the same way we operate with x approaching negative infinity. The y values would equal, remember we already have the equation here. Actually, we should continue. Down here, it's easier to connect them. As x approaches negative infinity, y will be 1 plus 1 over negative infinity over 1 minus 2 over negative infinity. Now, 1 over negative infinity will give 0 minus. 2 over negative infinity is 0 minus. So this will be 1 plus 0 minus over 1 minus 0 minus. So let's take this a bit further. So this would be 1 plus negative 0.000 something, right? Divided by 1 minus negative 0.000 something, right? So this would be 0.99999 divided by 1.00001. So this would be very close to 1, but a little bit less than 1. So we say 1 minus. So horizontal asymptote will still be 1 as x approaches negative infinity. But the y values will approach 1 from the less than 1 value. So the graph will be below the horizontal asymptote. And that kind of makes sense because look at this. Right? And there are going to be other things that can help us determine the graph, the shape of the graph of a rational function. So we will be helped a lot, by the x and the y intercepts when it comes to graphing a rational function. So it will be fun in overall. So this is how we find horizontal and vertical asymptotes. There are other easier ways that we'll explore together in the coming lessons. I will clarify one more time how to find vertical asymptotes now, the easy way. Step number 1, we have to factor the denominator. So we don't really have to go through the whole process of finding the horizontal asymptote like this way. This helps us understand where horizontal or vertical asymptotes come from. There are shortcuts to this, but once we understand how asymptotes are formed, the shortcuts will make more sense. We don't want to memorize things, we want to learn them. So a shortcut for vertical asymptotes is factor the denominator and then set the denominator to 0. So that means find the restrictions. And the restrictions of a rational function are actually the vertical asymptotes. So the vertical asymptotes will be in the form x equals the restriction. And a function, a rational function, can have more than one restriction or no restrictions at all, which means that a rational function can have 0 vertical asymptotes, 1, 2, or more vertical asymptotes. And this is it for this lesson. We'll explore more in the upcoming lessons how to find the vertical and horizontal asymptotes and other asymptotes as well. And I hope that you found this lesson useful. And I want to thank you again for choosing to learn from me. Have a great day.